Hello everyone, I am Serdar Enişte, Electrical and Electronics Engineering student at İzmir University. Today I am going to present my undergraduate thesis, Design of a Microcontroller-based Electromagnetic Water Flowmeter. Before starting my presentation, I would like to express my special thanks to my supervisor, Associate Professor Savaş Şahin, and my co-supervisors, Mr. Bahadır Yeşil and Mr. Alkın Gökçen, for their motivation and continued support. This thesis also presented in IPU IKSM 2021 International Conference of Applied Science, Engineering and Mathematics. In introduction, there is an increasing need for flow monitoring with different requirements, and there are a whole host of ways to measure flow, including electromagnetic flow meter. The purpose of this thesis is to develop an electromagnetic flow meter which can be used in water flow monitoring tasks, and in this thesis, an electromagnetic water flow meter is designed for flow monitoring tasks, and it is implemented with 32-bit ARM-based microcontroller. Now, starting with working principle of electromagnetic flow meter. Electromagnetic flow meter works based on Faraday's electromagnetic induction law. This law states that moving a conductor throughout the magnetic field generates electromotive force that is proportional to the velocity of the conductor, which is liquid in this case. And the direction of the electromotive force is perpendicular to the direction of flow and magnetic field direction. And this principle can mathematically expressed as E equals K times B times L times V, where K is the calibration constant, E is the generated electromotive force, B is the magnetic field strength, L is the distance between electrodes, V is the velocity, average velocity of the conductor, which is liquid. After deriving velocity from this equation, we can calculate flow using the cross-sectional area of measurement pipe. Now, here the designed sensor model can be seen. The model consists two coils with 1000 turns and 105 ohms per resistance per coil. Also, the thickness of coil wire is 0.2 mm, and the shape of the coil is designed in order to generate magnetic fields throughout the whole cross-section area of measurement pipe. The measurement pipe size is 20 mm, and the material used is Delrin, which is good insulator. In electrodes, non-magnetic 304 stainless steel material is used. Here you can see the inside of the pipe and part of the electrodes where they contact with liquid and sense the induced voltage proportional to the velocity of the liquid inside the pipe. This measured induced voltage processed using only some components of IFC handled signal converter of Krone. The processed digital output of this signal converter forwarded to STM32 development board to be converted back to voltage readings and to be used in flow calculations. In order to perform flow calculations, measurement algorithm inside STM32 applied to these voltage readings and flow values calculated at the end with respect to this measurement algorithm. Now, to make the flow measurement, coils of magnetic flow meter driven with 8.25 Hz square wave excitation signal. Using this excitation signal, magnetic field direction changes in every 60 milliseconds. Therefore, the induced voltage level changes, and there exists a potential difference between these two magnetic field cycles. This potential difference between cycles can be clearly seen when zoomed into one measurement cycle. Voltage spikes due to change in magnetic field extracted from the signal, and moving average filter applied to remaining cycle signal. Then the cycle voltages subtracted from each other, and mean value of subtracted signal is used in flow measurement. Now, velocity at measurement cycle 20 calculated as 1.8 meter per second, and flow calculated in cubic meter per second after multiplying velocity with cross-sectional area of measurement pipe. Then the flow unit converted to liters per hour, and the final value of flow at this cycle found as 2046.25 liters per hour. The designed model tested at various flow levels, and same measurement algorithm applied to each flow level. Here the results of zero flow can be seen. Then the mean of calculated potential difference between magnetic field cycles is found as 1.26 microvolts at zero flow, and similarly this value calculated as 0.08 millivolt at 1000 liters per hour, and 0.11 millivolt at 1500 liters per hour, and 0.15 millivolts at 2000 liters per hour. Results table. Now, in summary, after applying this measurement principle to number of different flow rates in the pipe, we get mean potential differences corresponding to each flow level. Here the points plotted in graph, and it is clear that there is a linear relationship between potential difference and corresponding flow level. This relationship can be expressed as flow equals to 1.32 times 10 to the power 7 times voltage minus 26.31. And in conclusion, potential differences between cycles corresponding to magnetic field is key factor to perform flow calculations, and signal to noise ratio drastically decreases when the flow is very low, and excitation signal has significant impact on output voltage waveform of Flowmeter. And according to test results, there is a linear relationship between potential differences in cycles corresponding to excitation signal, waveform, and flow rate. That's all for my presentation. Thank you for your attention.